Hello and welcome. Today we're going to be talking about improper integrals. And we're going to be specifically targeting the type of improper integral that's integrating over infinite domains. So what we mean by that is we want to look at integrals like, say, the one like this, 0 to infinity, this integral e to the negative x dx. All right, so if I were to look at the graph of this function, from 0, we know it's a decaying exponential, so it'll go down like that, and on forever. And we want to find, of course, the area under this curve. The big question we have, of course, is although e to the x goes to 0 at x going to infinity, does the area under the curve become small enough, become finite as x goes to infinity? Or is there infinite area? So that's the main question here, and we're going to find out that the answer is it depends on the function. In this case, for e to the x, e to the negative x, yes, it's finite. So such an area under the curve will be less than infinity. But now let's think about what we mean when we actually talk about this. So remember, it's a Riemann integral. It's a Riemann integral, which means integrability. Integrability requires that e to the negative x is continuous, and it also requires that AB, the interval, is finite. So clearly, 0 to infinity, this interval, violates that. So the trick to get around this is that what we're going to do is actually take the limit. We're going to take a series of integrals that go up to some finite value t, e to the negative x dx. And we're going to take t to get larger and larger. And then we're guaranteed, in this case, we're guaranteed this integral exists because t is finite. What we're really doing, though, is then just asking, once we know that this thing actually exists, then we can ask the question, the follow-up. There's a follow-up question. Maybe I'll write that in red there. And this is basically the follow-up question is this thing that exists, does it converge to a specific value? If so, we say it converges. Okay, that's a technical term that we're going to use when these improper integrals do in fact exist. Otherwise, we say it diverges. Okay. So it's really important we think of, again, just as we said before, we think of this integral as a thing that's over a finite domain. And then we basically take successively larger domains and see if all of those successive integrals end up tending towards some specific value or not. The idea we can't really just whole hog all at once define integral over an infinite domain. Okay, so let's go to our specific question we had. And we're going to use the fundamental theorem of calculus. Now, we're going to leave our limit sign alone. We're not doing anything to limit yet. We're going to calculate this integral that's very straightforward. And, of course, we're going to get I'm going to move this over slightly just to give myself a little bit more room. And note there that, of course, there's no t here. And so that simply becomes 1 minus limit as t goes to infinity, e to the negative t. And, of course, we know that that goes to 0. And so we find out the area under the curve is 1. So just to have a picture of that in our mind, e to the negative x, and the area under that curve is 1. Okay. So even though the domain is infinite, we can still get a finite area under the curve, even if even though, note that e to the negative x, remember, it's a strictly positive function. It never actually touches the x-axis. The graph is always slightly higher. Even then, it doesn't matter. The area under the curve is so infinitesimally small that even as you take more and more yardage of the x-axis, you're not adding enough area up to exceed 1. Okay. All right. So that's just the basic way of going about computing one. I'll go to the next page now and kind of just do a more formal statement about it. And let's now talk about a more basic integral. So I'll say we're starting at a and we're going to t, or sorry, undo that, infinity, and we have f of x dx. We're going to formally define that as the limit as t goes to infinity of the integral from a up to t of f of x dx. We want to know, does this diverge or converge? Okay, so now let's think of a new example. We're going to take the integral from 1 up to infinity of 1 over x dx. Okay, if we just looked at e to the negative x, but now we're going to look at 1 over x, like this. But we're going to start the integral at 1, and we're going to go up to there. And then we're going to, of course, look at that area under the curve, like so. And now we're going to express our integral this way as the limit of finite intervals, 0 up to t. Oh, not 0, sorry. 1 to t of 1 over x. The important thing here, or the thing that maybe might stand out to you, is the we're going to ask the question: is this going to be like e to the negative x? I mean, by and large, they kind of have a similar sort of shape. They're just these decaying functions as x gets larger and larger. But we'll see actually that there is a quite a big difference. All right, we're going to just continue to do our work here. Again, the limit symbol just is along for the ride for a little bit here because we're just going to do the calculus part. And we know that's going to be equal to natural log of absolute value of x. And then we're going to evaluate it at 1 to t. And we're going to get natural log of t. And I can take off the absolute values because we're all dealing with positive numbers here. Okay, natural log of 1, of course, that's 0. But here's the problem. Natural log of t going to infinity, well, that's going to infinity, so we're going to say this diverges. So although the shape of the curve is a decaying curve, just like e to the negative x, it turns out the area underneath this curve, it decays slow enough that you're always just adding up a little bit too much area, that in fact the area underneath that is infinitely large. Even though to the naked eye, if you look at the graphs, there's no way to tell that. You have to use the calculation. Okay. All right, well, we can try another one. Let's try this one. The integral from 1 to infinity. Well, 1 over x didn't work. Let's try 1 over x squared dx. Well, that's going to be, we keep writing our limit symbols, and we're going to have, of course, negative 1 over x. Oops. We're going to get 1 over 1 minus 1 over t. Of course, this part goes to 0, yielding the remainder, which is just 1. So now we're saying the graph of 1 over x squared which should, I will make a comment, that this goes to 0 more aggressively as x gets big relative to 1 over x. And it shows up in the area under the curve. It goes from an infinite area under the curve for 1 over x to a finite area under the curve for 1 over x squared. All right, so I think we're getting a sense for how to compute these. I will make a comment here. In everyday practice, for improper integrals, you don't always see integration with the limit t goes to infinity formally written. Mostly, we remind ourselves that when we evaluate at infinity, we are implicitly taking a limit. Okay, so what I'm saying here is that this limit symbol, in this section of the textbook, I want us to always to write it, but in general, I think people typically just implicitly are doing it, but they don't always have to write the symbol. So I'm going to just give you an example. I'm going to integrate one of my favorite functions. We're going to go from 0 to infinity of t e to the negative t dt. I'll use a different variable of integration here. Okay, so this function's a fairly straightforward one to integrate. T, and we take the antiderivative of e to the negative t, so we're going to have to do integration by parts. So we take the antiderivative, we're multiplying there still, and then it's going to be minus a minus, so plus. And we remember that when you do integration by parts, you have to evaluate there. And so again, we're now taking we're going to leave that infinity symbol on there. And again, remember that when we come time to actually evaluate, then we're going to be implicitly taking the limit. So now we have I'll leave that one alone for now. And now we have okay. So we've done all of the integration, anti-differentiation part of the integral, but now we have to go, and what we're going to do, though, of course, just remember that when you see these, we're going to be, take limit, like that. All right, so here's what we find. Now we evaluate at the finite value is going to be fairly straightforward. Here we're going to get a 0. And then we're going to add to that. Sorry, we're not adding. We're going to subtract 0 from that, because in the limit that of course is going to go to 0, and it of course goes to 0 faster than t goes to infinity. If we recall from L'Hopital's rule days of calculating that, and then finally what we're going to get here is plus e to the 0 minus the limit as t goes to infinity of e to the negative t. Of course, we know this decays off to 0. So the only thing we're left with is e to the 0, which is equal to, drum roll, 1. So a lot of our indefinite integrals, when they exist in this particular lecture, are all integrating to 1. I'm being a little cheeky here by doing that, but they don't always do that, of course. But I think it's kind of funny that we always have. Even though the graphs of the curves can be quite different. In fact, this case, the graph of the curve looks a little like that. It's got a cool shape. Again, it's one of my favorite functions. Again, the area under the curve is equal to 1. Okay, cool. All right. Now I want to talk about some technical things. We've done a bunch of calculations, and they're fairly straightforward. I think it's a fairly practical skill to do, to integrate to infinity. But it's a skill. I think there's one thing we have to be careful. One big warning. And that's when we have two-sided infinities. Okay, we really have to worry about this. Okay, let's now talk about this sort of. Now we talk about if we have a two-sided infinity f of x dx. It's tempting, but let's not do it. So I'll put a question mark here. Take a limit as t goes to infinity, and make this a negative t and then a positive t there, and then we have an f of x dx. but I want to X this out and say we don't do it that way. The way we have to do it is actually break it up into two separate limits. All right, and there's a really important reason for this. So t is going to infinity of, we'll go from 0, we can go from any value really. We can actually, I'll actually articulate that explicitly. And then also have a plus. The limit is, and now we're going to use a different letter. I'll use w, going to infinity, of integral of from a, or from negative infinity, we're going to w. And I also just have to now be mindful. I need to be clear on this. I was going a little fast. W is going to negative infinity of f of x dx. All right. And what's key about this is for f of x, the integral, to converge on the two-sided infinite domain to exist, both integrals above need to exist independently. And that's a big, big requirement that we're going to make for this. And you're probably wondering then, okay, well, why do we care about that? And the answer is pretty straightforward. Sometimes the two one-sided integrals will diverge in opposite signed infinities. Right, so what you get is just like what you'd see in L'Hopital's rule, an infinity minus infinity type situation. In such a way that the two-sided would make it seem as if it could converge. All right, so this is one of those big sort of red flags we have to watch out for as we kind of look forward towards looking at these things. So we can look at, I was going to look for an example of a function where we can have an issue like this. I think the classic one, let's actually first talk about, before that, I'm going to skip to the next page. Let's talk about, what about an integral that diverges? Let's look at another integral that diverges, and I'm just going to look at an integral from 0 to infinity of sine of x dx. Well, I can take the limit as t goes to infinity of, and I'll take the antiderivative of this, which is going to be negative cosine of x. Go to 0 to t. clearly this is going to be 1 minus the limit as t goes to infinity of cosine of t. And of course, this does not exist. Okay. Well, now let's consider the integral from negative infinity to infinity of sine of x dx. Well, if we, and this is going to be wrong, let's take the limit as t goes to infinity from negative t to t of sine of x dx. All right, well, we could do that just like before. And then, of course, we're going to get negative cosine t, or sorry, that'll be x in there, my bad, from negative t to t. And, of course, we're going to get negative cosine of t minus a minus cosine at negative t. My bad, I need to erase something here. That's not a plus there, that is a minus right there. Okay. Yeah. Oh, I'm getting a little tied up here. Oh, yeah, that's right. Okay. We'll go with that. It is plus. Okay, and then what we're going to get here, of course, is that that both of these, of course, does not exist together. Okay, so that's another example of even though we set it up wrong, we still got the an answer that was quite strange. All right, so in this one, I think I'll save the more complicated examples for a later video. I think we've covered enough of the basics, and I will cover some of the more subtle aspects of this in another video. Thank you very much.